Hi, Year 7. So we're going to continue talking about machines today, and we're going to look at the first type of machine, which is our levers. Okay, so we're going to start with a little video from Eureka.
Eureka!
The story so far. A machine is something that helps you use your energy more effectively. One of the simplest machines is the inclined plane, which allows you to trade increased distance for decreased effort or force. By doubling the distance you move a thing, you can half the force you need to exert. And now, the lever. If you're sitting on a teeter-totter, looking for someone to teeter-totter with, and then a big fat guy comes along, what do? Do you want to risk it? Now, there's an easy way you could have avoided that. Two easy ways, in fact. You could have either have asked the fat guy to move nearer and nearer to the middle of the teeter-totter until you balanced. Or else, you could have made a little adjustment to the teeter-totter before he sat down on it. And then, you would also have balanced. Both methods really boil down to the same thing. You see that support the teeter-totter is resting on? Well, scientists have a fancy word for that. They call it a fulcrum, which is simply Latin for a support or pivot. Anyway, whether the fat guy moves himself closer to the fulcrum, or whether you move him closer to the fulcrum by moving the teeter-totter, the result is the same. The distance between him and the fulcrum becomes less than the distance between you and the fulcrum. And that's the secret of successful teeter-tottering with people heavier than yourself. Or for that matter, the secret of the successful balancing of any object with any other heavier object. If you want to balance a 100 Newton weight with another 100 Newton weight, you place them both at an equal distance from the fulcrum, let's say 2 meters. But if you want to balance a 100 Newton weight with one that's twice as heavy, you move the 200 Newton weight nearer and nearer the fulcrum until it's in just the right place for the two weights to balance. Now you know how to lift a 200 Newton weight with a force of only 100 Newtons. It looks as if you're getting something for nothing, doesn't it? But you're not. Don't forget that the 200 Newton weight is nearer to the fulcrum than you are. How much nearer is it, in fact? 1 meter? So the distance between you and the fulcrum is exactly double the distance between the 200 Newton weight and the fulcrum. That means that you have to move your end of the teeter-totter exactly twice as far as the weight moves. You exert a force of 100 newtons through 1 meter in order to lift a weight of 200 newtons through half a meter. What you win on the force, you lose on the distance. Sound familiar? Of course. It's precisely the same principle as that of the inclined plane. When you double the distance, you can half the force. This is true whether you're using an inclined plane or a teeter-totter. Only we should stop calling it that, because when we use it to make work easier, it's really another sort of simple machine. It's really a lever. Yes, a lever. You use levers all the time, things that give you leverage. After the inclined plane, it's the commonest simple machine in the world. Even cavemen knew about levers. Not to mention old Archimedes in ancient Greece, who was actually the first person to state the principle of the lever. The longer the arm of the lever to which force is applied, the less that force need be. In fact, he got so excited about this one day that he said, "Give me a fulcrum on which to rest, and I will move the earth." That may have been taking things a bit too far, but at least you now know enough to go down and apply Archimedes' principle of the lever to your teeter-tottering.
Right, so, yeah. For starters, that's a Canadian video, so a teeter-totter is what they call a seesaw, just one of those little weird eccentricities. And it's a very old video, so that's why they're still allowed to use some of those terms that we might not use much any day these days. Alright, let's go through there and have a look at what they've been talking about here. And we want to look at levers. So we're on page 5 of our book. Okay. And we want to put down these notes. So at the top of the page we want to write down that a lever is any kind of beam or rigid rod. And that's this bit in yellow here, running all the way across. If it's flexible, that changes the properties a little bit. Now, in reality, if you put enough effort and load with the fulcrum in the middle here, it's going to bend, okay? But we don't have to worry about that for this topic. We talk about the load being where the mass that we're trying to move is, or the object we're trying to move. Alright. Now, in this type of lever here, it may well be that we've got effort on both sides, we're pushing on both sides of it, or we're generating a force on both sides. That's fine. Okay, it's just a way to define what we're talking about. And so the effort's the other side. Alright, and this gives us our three terms, our L, E, and F. And our fulcrum is the point of rotation. And that we quite often show as a triangle, but it can also be a circle, it can be like an axle, some sort of hinge. Okay, all of those things are going to be fine for us to use as a fulcrum. Okay, but it's the point where the lever pivots. Okay, so around here it's going to move. So this is going to go down, that's going to go up, or that's going to go down, and that's going to go up. Alright, so make sure you've written them down on page 5. Now, we've got 3 types of levers, as you can see in your notes. We've got a first class lever. For a first class lever, we have the effort, the fulcrum's in the middle, and then the loads on the other side. So the load and effort sit across the fulcrum. And you want to copy this diagram into your book. Okay? And a good example of a first class lever is the seesaw. Alright, if you need to, remember guys, if you need to, you can pause the video, okay, to make sure you get all the notes down. So I'm going to keep moving on. Alright, a second class lever, and here's an example of a wheelbarrow. Not sure why he's needing to wear a suit while we're carrying a wheelbarrow. I don't tend to, but you can if you like. And here you notice that the fulcrum is on one side, and the load's in the middle, and the effort's on one end, okay? And so the object is going to move around the fulcrum here. Alright, third class lever. Here we've got the fulcrum near the end. The force is in the middle, or the pull. Okay, so the effort's in the middle and the load's at the end there. And a great example there is a fishing rod or your arm. So if we think about our arm here, okay, and I've got my arm here. Alright, if I'm moving it, okay, backward and forward, then the fulcrum is down here at the elbow. Okay, or the effort's in here, and the load is up here where I'm holding onto something. Alright? And so that makes that's a great type of third class lever. Alright, so now that we've got that information, I want you to complete the worksheet on page 4. I want you to write down what type of lever you see in each of these examples and where the effort, the fulcrum, and the load are going to be. Okay? And pause the video to do that, finish it, and then start playing again. Okay, and we're back. Alright, and here's our answers. So hopefully you got them all right. And I'm going to jump on. Okay, now, as we talked about in our first video, all machines have a mechanical advantage. So we want to have a look at how the mechanical advantage works for a lever. And there are 2 things we can do. So the first thing we have to worry about with any kind of lever, especially a lever where the fulcrum's in the middle, is that the 2 sides are balanced. Okay, and by that it means it's not moving. Alright, and to do that, the work becomes balanced. Now work is the force times by the distance. Okay, so here the work is going to be 10 times 2 or 20, and here it's 20 times 1, which is also 20. Okay, and because the work on both sides of the fulcrum is balanced, okay, or the 2 objects, the they're balanced, we're good. And then we can work out our mechanical advantage. So, we've got two ways of doing this. We can use the lengths. Okay? And if you divide the longest length by the shortest length, you get the mechanical advantage. So in this case, we've got 2 divided by 1. So the mechanical advantage is 2. Or we can use the forces. And that's what we talked about in the previous one. Okay, and we were talking about the general example. We can use 20 divided by 10. And if you put that in a calculator, you get 2 as well. Okay? Now, one thing to remember. Weight is a force, but it's the mass times 10. So this object here actually weighs 1 kilo. This object here weighs 2 kilos. Okay? So we always need to make sure we take the mass and times by 10. Now what I'd like you to do is pause the video here and write yourself a little summary on page 3. So if you go back to your page 3 in your book, you'll find it's the flip for levers, and you can write down how to find the mechanical advantage for levers. You don't have to write the equation. Okay, you might just want to write yourself a short little sentence for an easy way to figure it out. Maybe talking about the length or the force. Alright, now I'm going to jump on, have a look at one more example. Okay, and here we've got, what type of lever is this? This sort of thing? Okay, so this here is a second class lever. There's our fulcrum. There's our load. There's our effort. To work this out, we need some information. So let's start by looking at the load here. Okay, and the load is 18 kilograms. Okay, now we need to convert that into a force. So to do that, we need to do the weight equals the mass times by 10, or 180 newtons. Okay, so that means the force pulling down here is 180 newtons. Now we're going to figure out how far away it is from the fulcrum. Okay, and it says here that's a meter away from the fulcrum. So if we take the 180 newton force and we times by the distance, we get the work. Okay, which would be 180 newton meters. And that's how we write that unit there. It's a combination unit of these two units here. Alright, now over here, this load will have to balance this work here. So what we're going to do is we're going to say that force times distance equals work. So we did that here. 180 newtons times by 1 meant we had our work. And here we've got an unknown force, and we're going to times that by 6. So let's see, our work is 180, and our distance is going to be 6, so we don't know what our force is. So now we can work out, so what times by 6 will add up to 180? Okay, well, you guys have done a little bit of algebra, so you could do a flow chart for this if you want. We could balance both sides, or we can figure it out by a bit of guessing, and we come up with 30 newtons. So this force here is going to be 30 newtons. Now, can we figure out the mechanical advantage? Yep. I'm going to use the biggest force divided by the smallest force here to figure out the mechanical advantage of this thing. So I've got 180 divided by 30. Okay, which equals 6. So the mechanical advantage of this lever here is 6. Okay, so we've talked a little bit about levers. So we hopefully know that a lever, and when we're talking about levers, we talk about the effort, the fulcrum, and the load. Okay, that a lever is a rigid bar that moves. Okay, and it's a simple type of machine. It's one of the two basic simple types of machines that we're going to look at. And I hope that was very helpful.